Thanks for that introduction. And I don't speak Polish, but as a little gesture towards our local accommodation here, I've chosen some color set representing the city colors of Krakow. I think it's a little bit more darker, the blue, but I needed to have something readable. So I hope you can. I hope you can excuse that small mistake. All right, let's dive directly into this topic. So functional mocking. Presumably all of you know what mocking means in object-oriented programming. Quick show of hands. So it's not about making fun of the code, also sometimes it feels like it, but what is the actual definition of mocking? So here's what Wikipedia says about mocking. In object-oriented programming, mock objects are simulated objects that mimic the behavior of real objects in controlled ways. And that's kind of funny because it's some sort of overly specific definition because it already says object-oriented programming right here. So who am I to talk about functional mocking? I mean, there's no such thing, but bear with me for a little. So what does mocking actually look like? So I've chosen some examples from the front page of Scala mock, which is a popular mocking framework in Scala. I mean, mocking is not that popular in Scala, but the most popular one is the Scala mock. And let's say you're writing a class for turtle graphics, and now you want to check whether your function, which uses this turtle object, so this drawLine function is supposed to be implemented on top of turtle, and now you want to test whether this drawLine actually works correctly. Then you would create a mock object and tell it, well, I expect that this function calls setPosition, then calls forward, and then calls getPosition, and then you say, well, I'm expecting these arguments, I'm expecting that argument, I'm expecting that return value. And then you call that function, and Scala mock will actually try to figure out if all these function calls happened in the right order, in the right way. And in some sense, you can see it as a generalization of unit tests. In unit tests, you usually test the return value, and here you can also check some intermediate results or some intermediate calls. So that looks quite nice in theory, but why not? Why don't we mock? So here's what Martin Fowler has to say about it. Have a look. And this is a very fundamental problem about mocking because it is tightly coupled. And once you change the implementation of your of the object you're mocking, then you have to rewrite all your tests, and you have to rewrite them significantly. For example, consider you're making some optimizations in your code, which drastically reduces the number of calls you're doing. Then you have to go through every single test which uses that function and have to rewrite it. And you don't have to just change the values in there, so just tweak them a little bit, but you have to rewrite the whole set of function calls. And what's even worse, if you look into the implementation of these kinds of mock frameworks, you can look at Scala mock, you can look at Mockito and whatever they are called, and if you actually open the source code, you will find yourself like this. So it's kind of like an adventure game. You're finding new meta-programming facilities on every new file you're opening. And so that's why in the functional world, this concept of mocking is not really popular. We don't do that much reflection. We don't do that much meta-programming. We just try to do it with functions. So back to my original point, functional mocking, there's no such thing really. So during research for this talk, I went through a couple of Google searches and typed in like Haskell mocking framework, functional mocking, and there were a couple of Stack Overflow questions on that. And basically for every single of these questions, the answer was, don't do that. Like there's no mocking in functional languages, just use a higher order function or something like that. And I mean, that's kind of okay if you already know functional programming, but if you come from somewhere else and don't know how functional programming works, that's not really good explanation because I mean, if you ask me, how do I do mocking in functional programming? And I answer, well, don't do that. There's no such thing. Then you still don't know how you would achieve the same result without mocking. So instead, I'm going to talk about a couple of techniques which are unique to functional programming languages. And these techniques combined avoid the need of mocking altogether. So basically, these are techniques to reduce the coupling in your program. So this talk could as well have been called functional decoupling and not functional mocking in that sense. So what are these set of techniques? So we've heard today that functional programming is ill-defined in another talk. I don't quite agree. I think there's actually a good definition, but not everybody agrees on that definition. So I'm going to give you my definition here. And I think this is, these first 3 points are very important for functional programming. And the fourth one is kind of a corollary to that. So we first have the separation of data and operations. So we can define data types in a different module somewhere else. And the operations can be completely independent of that. So we can have then in separate modules, and you can swap out operations. You're not like in an object where you have a fixed set of methods. You can just always extend your operations every time. And we even have ways to deal with extension of data. So we can even add new cases to data types in several languages, and in other languages there are tricks to that. Also, we have parametric polymorphism, sometimes known as generics. So abstracting over types is really pervasive in functional programming. So it's not only in Haskell, but also in Scala and in all those other languages that we always try to write the most general type for a function. And during that, we actually notice that we don't care about the type of the element in the list. It's just for any type of list. Also, higher order functions. So no matter which source code file you're opening, there are chances that you will find a higher order function in there because it's so tremendously useful. And as I said, as a corollary from that, we have lightweight interpreters. And this basically means we can define domain-specific languages all the time, and interpreting these domain-specific languages is really easy. So if you have ever written a parser for something, you have already done that. It's a lightweight interpreter. You're parsing something into a data type, and then at the end, you're doing something else with that. And actually, parsing and having a data type for some expressions is going to be my running example today. So here's a data type for arithmetic expressions. This is really simple. If you don't read Haskell syntax, don't be confused by that. It's just you can just read it as an expression is either a literal with an int value, or it's a variable which has a name as a string, or it's a sum of two other expressions. So there's really nothing complicated here. And once we have a value of that type, we can ask the system to evaluate it. And of course, we have variables, so we need to assign some values to their variables. And we do that with a map. So we just say we have a map from string to int, and we get back not a plain int, but a maybe int, because the map might be undefined. So if you're using a variable called z, and the map does not provide a key which is called z, then you will want nothing back. Or maybe an arrow data type or whatever. But this doesn't really matter, just not a plain int. So that's the basic idea. So this is really boring. This cat is completely unimpressed by that. You probably have written that 1,000 times over and over again. So let's beef that up a little bit. So the first thing you should ask here with that code is, why are you using a map? I mean, map is a pervasive library in Haskell, but what if I want to specify another function? So what if I want to specify something which computes the value on the fly, like the length of the name of the variable? I mean, go crazy, do whatever you want. So in essence, a map is just a function from a key to a maybe of its value, of the associated value. And we can just replace it in the first step. So we can say, instead of taking a plain map, we just have a string to maybe int. And that's a higher order function already here. And this is really one of the first steps you should do if you're writing a library and you're taking a map from someone else. And your library is not really about maps. Then you should ask yourself, why am I using a map here? I could just take it as a function. And that's all nice, but we're still not done. So next thing you should ask is, why am I talking about integers here? I mean, those are the machine integers. That's not really useful. They overflow. And why am I not letting the user decide which kind of literals I want? So let's generalize. So now we have our first parametric data type in this talk. So we say, we give it a type parameter, which gives the type of the literal. And of course, we have to add this a every time we use it. And for the evaluation, what we're saying now is, we can evaluate any expression of type A as long as we know how to deal with it as a number. So num is a type class in Haskell which specifies the common arithmetic operations like addition, subtraction, multiplication, all that stuff, and different conversions. And what we're saying here is that we don't care about this A, we just care that we can add it. And that's really all we need, because now the user can just use floats or the arbitrary size integers or whatever. And basically, up until this point, the code has not changed at all. I mean, it's still exactly the same code. We didn't have to change anything between here and there, because the plus operation in Haskell is already generalized to anything numeric. Okay, one step more. Why are variables strings? I mean, string is a data type which contains an infinite amount of values. So you could have any string, for example, the empty string. But no sensible programming language would allow an empty string as a variable name or whitespace, unless you're programming in whitespace. But you usually want some different type for your variable names. You want a symbol type which only contains alphanumeric characters or whatever, doesn't start with a digit, whatever. And you don't really want to represent it as a string. You want to represent it as a different type, because that's also what we do all the time. We have a whole set of values like integers, and then we partition it into different spaces, or we take a subset and put it into a new type so that we don't confuse the whole values. And that's what we're doing here as well. So we're saying, okay, just generalize it here as well. So we give a new type t for the name of the variables, and replace all these string occurrences with t. And we also didn't have to change any code here. It's naturally already there. We didn't use anything specific about strings, just the way we didn't use anything specific about integers here. Okay, one more step. Why are we always even using maybe? I mean, we could just write that with any kind of monad. Because let's assume your variables are in a database, and you want to call your database to get the value of the variable. So you wouldn't have a maybe there, you would have an IO of something, because you're using Haskell, so your function's up here. And the important bit here is that also you don't care about maybe, because that maybe just came from here. That's why you got the whole maybe in the end here. But you are not using, you do not return nothing by yourself. You just take whatever this function gives you and return it. So we can just generalize it to any monad. And this cat is totally confused now, because like we started with a simple design which everybody could read who has no idea about Haskell, and now we have something which uses monads and whatever. Like, why are we even doing that? So here's my next slide. Why this complexity? Why are we even bothering to do that? I mean, the first thing already works. I mean, if the only thing we're working with ints and strings, we could have just used the first version and then generalize it. And there's this acronym called YAGNI. You ain't gonna need it. And here's the definition by Ron Jeffries. Always implement things when you actually need them, never when you just foresee that you need them. And we just did exactly the opposite. We just thought, like, what could you possibly want about this library? And let's just generalize it in a way that we can actually, that the user can actually do that. So from this point of view, it was a terrible idea. But it's actually a good idea, because we also gain something. By abstraction over num, we have actually assurance that we don't mess around with the values. So we can't just insert a null or a 1 or whatever in there. And the caller knows that only the num type class influences the behavior. So we do not fiddle around with the values ourselves. We just take that back what the num type class gave us. And it's the same for the abstraction over monad. So we get uniform data access. We can plug in maps there. We can plug in a database lookup. And we can even read from standard input. Like, I mean, who stops you from doing that? Like, you can just put an arbitrary operation as long as it gives you some IO int or whatever, or IO float, or don't care. And if you take this data type we have just defined with these two parameters and you register some more instances, for example, you can make it traversable and you can make it a monad itself, and you can even gain some more from that. So, for example, let's say you have to write these three functions, and these are really common if you're writing some sort of small DSL, some sort of if you're dealing with expressions. So, for example, this function, it takes an expression, gives you all variables which appear there. For example, if you want to make that code analysis, you want to know if the variables are even accessed. So you have a set of variables, and you want to check whether the variables occurring in your expression are a subset, or if, like, which relationship are they to each other. And then you want to have a function which takes an expression A, and the variables are maybe undefined, because they may be, you've spelled them wrong, or they do not actually exist, or whatever. And you want to get back a maybe of an expression t where these are defined, and you want to get a nothing if any of those variables are nothing. Or you want to substitute variables. So you have an expression at, and you want to splice in some other expression for your variables. For example, if it's a function call, you want to do substitution. And if you look at all these functions, they are all some sort of traversal. So you would write a case analysis on your expression here, you traverse that stuff, and here you traverse again, and like, seriously, why am I repeating all that code? And if you register your data type as foldable and monad, you get all these functions for free, basically. So you can just use them from the Haskell library. And I'm not kidding. This actually compiles. If you make your if you register the correct instances, then you get all these functions for free. This is, for example, just monadic bind. It's just if it's a monad, you can just bind something into the positions where the variables are, and you can just use toList, for example, from foldable to get all the variables, all these positions. And this is obviously just a small example, but you basically have the whole power of the data, foldable data traversable library in Haskell, and every single other library in Haskell which is abstract over foldables. So you get this complete power, and it's like at least 20% cooler than your old code. And you can even do aspect-oriented programming with that. So for example, what if you want to log the variable access in evaluate m? So let's say you want to check the performance of your evaluate function, and you want to check whether each variable is only accessed once, or maybe, I don't know, whatever you can imagine. You want to check something about the number of variable accesses. How would you actually do that? And the way we abstract our monad, it's really easy to do that. So let's see some demo code. So this is just this data type I've defined earlier. And this is the evaluate m function. As you can see, it's not really that difficult, and it reads a little bit like an imperative program. So this code, if you just look at that code, you can kind of see what it does. So it traverses the data structure and does some operations, and this is the most general type you can give that function. And then we have I have predefined a map which assigns x to the value 0 and y to the value 1. So that's just a sample default variable assignment. So let's run this. And we can now just say evaluate m with this var tab. And let's define an expression first. So let's say expression equals the sum of x and y. And let's just evaluate that with the var tab. And we get just 1. On the other hand, if we had a set here, then you would get nothing because the y is not defined. The set is not defined. Anyway, so what if you now want to want to check these variable accesses? And there's a monad in Haskell for that. It's called the writer monad. And the writer monad is something which is kind of like a logging framework, just that it's really simple and it doesn't need 5 megabytes of dependencies. And I've written a function which takes this here, this var tab, so it wraps an accessing function and calls a function which is called tell. And imagine tell is called log, and then you will know what it does. And I can just wrap this function around, and it will just work. So let's define it again. And say evaluate m, wrap log, var tab, this expression. And now we get quite a huge error message because I have not actually specified what kind of writer monad I want. So I'll just force it to a specific one. But that's just a technical detail, and if you look into monad transformers, you will get that explained. So there's this is all learnable. So we just run this. And now we can get back our original value of 1 and additionally a log of which variables have been accessed. And this all without changing the code. You just had another function called wraplog, and you put it in there. In the end, you tear it apart with this run writer thing, and that's basically it. So that's really nice. And if we had followed the Yagni philosophy, we wouldn't have been able to do that. Without abstracting early in your design process, many abstractions and concepts actually stay hidden. And the Yagni way of thinking is actually a limited way of thinking. So I would kind of advise against doing that. And it's especially important if you're building libraries. So next time you're writing an interpreter or whatever, DSL, think about generalizing your types generalizing the operations over monads, over numbers, or whatever, don't give concrete types, because then you will maybe find a library. If you find yourself wanting to write a function about that, you will most likely find out that this function already exists, and you can use it because your type is so general. Okay, let's have a quick interlude here. Let's go back to one of these pillars of functional programming, namely immutable data structures. And I've hidden a little Java code in here. So this is one of these popular Java beans. So it's a class for persons, and it's very simple because it only has a name in there. So if you want to update these objects, what you do in Java is you can just get your root bean, use this kind of fluent interface, go all the way down, and you can just call set. And you have a basically a nested data type, and you can just use getters and setters to update some bits below in your hierarchy. Now, what does it look like? The same code in Haskell. So let's define some data types. So we have a company, and it has an IT department, and it has a human resource department, and every department has a boss and has a budget, and every person has a name. So this is from the Java code earlier. I didn't write that as Java code because it wouldn't have fit on my slide, but you get the idea. So let's say we have a company value, and we want to update the name of the boss in the IT department. Right? So we want to have something of that, and we want to update this, in that. So in Haskell, you could write it like this. And this is horrible, because this is like quadratic. If you go even deeper, you have to repeat yourself quite a lot. And yeah, this looks horrible. You don't want to write that. Luckily, some clever people have come up with a way to work around that. And this concept is called co-state, co-monad, co-algebra. No, I'm just kidding. But it's the highly theoretical variant of Java beans. So what is the essence here? This concept is called lenses. And what lenses do is basically allow you, they give you a way to focus on a specific subpart of a data type. So let's say your company is the whole thing, it's A, and B would be the department. And then you can obviously specify a function which takes the company and gives you back the department. And it is also possible to write a set function which takes the company, takes an updated department, and gives you an updated company. So this is really just the essence. It has a get and a set function, and you can already do a lot with that. For example, you can compose them. So if you have a lens for a company, for a department inside a company, and you have a lens for a person inside a department, you can merge these together and get a lens which gives you the person in a company. So as an exercise, you could just think about a little how you would write the compose function. It would look a lot like the type would look like a lot like the dot operator in Haskell, like function composition. And but this formulation already gets you really far. But we can take that even further. We can throw Edward Kmet on it, and what will happen? You will get this formulation. And I mean, look at that. It doesn't really look like that anymore, but it's really a more general version of that. And you don't have to understand that. I don't, in full, I mean, at least not in full. You can see here kind of that it's a function which takes the whole thing and wraps it into some effect or whatever, and then you get something back or whatever. So it is some sort of updating function which is wrapped here. And what can we do with that? What does that give us? Well, it gives us a function composition, so we can just use these lenses as plain old functions. So this is really actual code which works. So you can if you have a lens for the IT department, you can compose it with the boss of this department and the name of that person, and you just call set on it and give it a new name, and it will give you an updated company. And this is regular Haskell function composition. So with the old formulation, which is not really generic, you couldn't use the regular function composition. You would have to use a different operator. And with this better version, you can just use regular function composition. And that's really nice because that's another example of the more you generalize, the better libraries you can use. Because now it's just a plain function, and all the stuff working on functions also works in your type.
Can you go back one slide?
Yes.
So would the naive formulation also not have a A to B and from B to C, then you need 3 types. So is that also not an issue for the bit of the naive form?
So you can just, I mean, it works also for the naive version, but the point is you can't use function composition for that. You have to, so the composition function for this, it looks a little bit complicated. It's like 3 lines of code, and here it's just 1 line, basically. Yeah, and also you get mocking for free, so back to topic, because lenses are ordinary functions, so you can swap them out. Let's say you have you're dealing with a module which gives you all these data types for companies, and then in the next version you decide you want to have additional layer of abstraction. So, for example, departments are organized in department groups, and now you have old code which looks at the IT department, and now you would need to update that code because you have now the IT department is in the infrastructure group or whatever. But with lenses, you can actually give a kind of intermediate version of that, which just composes these 2 things together, and it works like in the old code. So you can easily adapt to changes without affecting user code at all, because now it's kind of virtualized version of member access, and the user of this lens doesn't actually care whether it's an actual field in an actual record or if it's a database access or whatever. The client just doesn't care. I have another picture here. This is what sometimes people think about when they say you should practice Yagni. So you shouldn't bolt on stuff on top of other stuff so that you get a fragile composition. But I'm actually arguing in favor of pausing, thinking hard about your problem, generalizing, and then you don't even need to think about tacking on because it will be one whole thing, basically. Okay, calculator again. I hope you're still with me with that. I'm going to update this example now to different syntax. Who of you is familiar with GADTs? Okay, good that I have an additional slide for that. So this is just the same data type I had earlier. And let's have a look at these constructors. And in Haskell, constructors can be used just as ordinary functions. So you can, for example, ask the type of the sum constructor. And you will see it's a function which takes 2 arguments and produces another one. How it does that internally, you don't care. It's just like a function. And you can actually rewrite your data type in that way. So you can give explicit types for your constructors. And here's what it looks like. And it really reads kind of the same way. So you say a literal is a function which takes an a and gives you back an expression at. And a variable is a function which takes a t and gives you back an expression at. So that's really not complicated. I have this slide because now I'm doing some advanced type hackery and you can't express it with the old syntax. So here's the new syntax. So far, expression at, so if you have value of that type, you only have literals of type a. So there's no way you can have ints and floats in the same data type. The type a is constant in the whole expression. You can't even change it. And sum is a nice operation because it takes 2 a's and gives you back an a. It's homogeneous. But what if you want heterogeneous operations like even? Even takes some integral value a, so something which is an int basically, and gives you back a bool. You can't model that because you can't really, you would need to change this type here. And actually with GADTs you can. So let's simplify that a bit, get rid of variables because we don't need them anymore for the purpose of this example. So we just have a data type which has literals and sums. And now we generalize. We change this a here and give it this num constraint explicitly. And then we add another constructor which surprisingly somehow changes the result type in here. And this is actually a Haskell syntax, so you can do that. And what it means is for any a, if you have a value of expression a and you have proof that it is somehow an integer, then you can get an expression bool. And you can read that as, if I have an expression of type a somewhere in my code, it will produce an a. Right? So how do you even, this actually works. And then just for the fun of it, we can add another operation, for example, a cast operation. So now you have bools here. What do you do with these bools? You can't add bools together, but you can add another case which tells you how to cast a bool to something else. So for example, if you want 0 for false and 1 for true, you can just wrap this even call into another call of cast give it a function which translates your bools into integers, and then you get back an integer, and then you can take the sum of it. So this is really nice because now you have kind of a strongly typed calculator at your hands. So by construction, you can never produce type incorrect computations. So this is really important if you're building a compiler or something like that, or for DSL, which is a little bit more complicated. And you don't need to care about failures in your evaluation. You just give these additional types, and then by construction, you always have a valid expression at your hand. So we now have a data type which represents these arithmetic operations. What can we actually do with that apart from evaluating it? So I have some ideas. So you could print it. You could count the operations in there. And you could optimize it. So for example, if you know how to fuse some operations together, you could just do that. And let me tell you, we're just going to do that. So here's this data type, and the evaluate function, I've toned it down a little bit again, no monad anymore here because I don't want to cram all different things into this small example. And we can now write an optimize function here, and basically the most trivial implementation you can do here is you could say optimize x equals x. This will always work because you can always do the identity transformation. Let's just do a simple one here. So for example, if we have a cast of a literal, what can we do with that? Of course, we can just apply that function directly to the literal. And now if you know a little bit about GHC, then you know that it's already quite heavy work going on there, because you have this cast f, and it is some non-standard data type, so you have some changing types in here, so the compiler will actually try to come up with new type variables and try to figure out if that's all still correct. But the good thing is, if it compiles, it worked. So we can just try it. You have an expression, let's say cast, and let's say, I don't know, lambda x, if x then 1 else 0, and then you have literal true. Oh, I'm not writing Scala, I'm writing Haskell. So we now see we have a cast of a literal, and if we just call optimize on that, we get just a literal back. And this transformation is actually type correct by construction, so we can't make any mistakes, so just go crazy with the optimizations here. The compiler will check that they are correct. Okay, so I still got a little bit of time for my last point, and the last point I'm going to make is about I/O. My hobby, asking Haskell developers about the meaning of I/O, and just eating some popcorn while they try to come up with an explanation. Because I/O is deeply magic in GHC. So you don't really know what's going on. You're at the mercy of the compiler implementers. And it's kind of funny to see because it could have been different. And how could it be different? So what is actually the essence of I/O? What do you mean if we say I/O in Haskell? And IOA is, I like to imagine that, and I also like to explain it to students. IOA is like a recipe for A. So assuming you have a recipe for spaghetti with tomato sauce, then if you open this recipe in your book, you don't actually have spaghetti with tomato sauce. You still need to follow some instructions, and then you get, as a side effect, you get your spaghetti with tomato sauce. And it's the same way in Haskell. If you have IOA, you don't have an A value at your hand. You have a recipe on how to create an A. And basically, it's just a representation of this computation. It's a representation of how you produce your spaghetti. And the point of I/O is that this adds some interaction with the real world. So instead of fetching some ingredients for your cooking, you fetch some data from a database. So that's kind of the same thing. And the important bit here is that it's a representation. So the compiler implementers can choose whatever they want here. In Haskell, I/O means that it can contain all sorts of effects. It's kind of the super monad, which has all sorts of things in there. Asynchronous computation, network access, terminal I/O, whatever, you name it. Additional in GHC is opaque and non-inspectable. So if you're calling a function of type IOA, you can't really introspect what's going on in there. You just can execute it. But as I said, a better world is possible. So we can actually make it a DSL. So we have this calculator example, which is a data type with one constructor per operation. And we can also define a terminal application, which is a data type with one constructor per operation. So can we do that? What kinds of operations can we do in the terminal application? So we can read from standard input, we can write to standard output. We could open files, read from files, and yeah, whatever, what the terminal application even does. And I'm going to focus on this bit here. And if you go tomorrow to Runar's talk, he might talk about how to combine these effects into, so if you write something for this, how you can combine these together. Are you talking about that? Probably not. Okay, then you have to look at Runar's old talks, because he talked about that. So we have just this small data type here. And this is really similar to this data type we've seen earlier. We have something for terminal computations. It produces some value A. And what can we do here? We can read a line, which will give us a string, and we can write a line, which takes a string and gives us some unit back. And this is really, that's really it. Now we just need to do something with that. I mean, this data type by itself doesn't do much, so more demo code. So I am importing some pretty fancy stuff in here. You don't need to know about that. I'm just showing you the result here. And if you want to look at the sausage factory, I can give you some hints about material you can read. So here's our data type. It's just copied verbatim from the slides. And I've added a type alias, which basically wraps our terminal A into something else so that we can use it. And then we also write some convenience functions, which do some heavy lifting. It's not really that heavy, but. And now, just by writing that, we can already use it. So let's say we want to have a function, an application, which reads something from the input and immediately writes it out again. We have read line, and then write line immediately after that. Oops. And this already compiles. So this is already a monad. And we can ask for its type. And we can see that it's some weird thingy containing a terminal and producing a unit value. But of course, you can't do much with that because we haven't yet specified how to actually execute it. But just from writing down that definition, you can already compose your operations, and you could even pattern match on that if you want to. So how would we run that? Of course, the first idea would be to compile it to actual I/O of Haskell. So if you see a read line constructor, we would actually call the getLine function, which is primitive in Haskell, in GHC. And if you have a write line constructor, we could call putStringLine of S. So does that work? So we define the same app, and now we say, what's it called? Oops. Run free IO. All right. So we say run free IO, and then we give we say in which direction we want to run it, so what do we actually want to interpret it to. Then we give our app, and now it will execute it in GHCI, and I can type in ABC and get ABC back. Okay, let me just show that again, top of the screen, so typing in, getting something back. And this is our completely abstract representation of our computations, and this is a way which tells this interpreter how to interpret it. And we can even define something else. So assuming you want to write tests for this code, for your terminal applications, and you don't want to actually run it with standard input and standard output. Let's just say you want to run it with some fixed input data and want to check if you get some fixed output data back. And you could fork a new process and intercept the standard in and standard out in some way and then check if it's compliant, but you don't need to do that. You can actually write a different interpreter. So if you can see, this function below here is structured in the same way as this function here. So we're taking some terminal value, and now we don't interpret it to I/O, we interpret it into the state monad. So this says, if you want to read something, let me get the input here and remove that input from my buffer. And if you want to write something, just add that to the buffer at the end. And yeah, so we have basically a value of which is a tuple, where the first element is the input which is remaining, and the second one is the output we have written. And now the very same code we wrote still works. So if you define that application again, so this is really the same application we defined previously. And now if we say run free IO, and now we say console IO to state, we used an app, we can get a different interpretation. And of course, we need to run that somehow. It's a state monad, so we can't execute it immediately. We have to look for the type, so there's some state going on. So we have to give it an initial state. So we use run state t. Oh, I have to give it another. Okay, let's give it some input. So we say we have ABC as an input. We have an empty output in the beginning. And now we can see the input has been consumed and new output has been produced. And we can try that with different examples. So assume we already have some output, then you can see that this output is preserved and appended to that. And if we have some additional input, which is not being read, then this will still be there. So this is using exactly the same application you wrote, using a different interpreter, and you get a completely different result. So you can easily test your code. You don't have to jump some hoops to intercept some process communication. You can just specify a different interpreter, and that's really all there is to it. And you can turn that even up a notch. This is code from one of my colleagues, which is used for testing homework. And basically, he has defined a completely own definition of I/O with some internal data, like how many files are open, in which directory am I, and all these things, they are completely virtual. They have no relationship to the actual system whatsoever. And if you now wrap this into this free monad, which I've shown you, which I've told you to ignore in the code before, then you can actually generate a completely an I/O system which stands completely on its own, which is completely independent from the I/O representation in Haskell. So conclusion, FP provides a set of techniques for abstraction over evaluation. Use them. And as Donald Knuth not said, premature evaluation is the root of all evil. Questions? Yes, yes. So the question is, if I execute my code with different interpreters, I end up with different ways I have to call them. So that question, yeah. So the way, you still have to write the code for the actual invocation. So if you're running in production, you have another module, so you have your module which defines your application, and then you have a module which calls it in one way for production, and then you have another module which calls it in another way for testing. So basically, that's the idea.
Because we use the cake pattern a lot, and this introduces a lot of boilerplate in the end just because of testing purposes.
Yeah, it does add some boilerplate if you have multiple invocations, but in the end, I think the benefits are worth it because you save code in other places, basically. So that's how I would phrase it. Yeah?
I would rather to recap or maybe to clarify my understanding. So, as I understood, let's say a few months ago in the London was the Scala Exchange conference, and there was a man whose name is, I don't remember, from the US, and he was talking about the usage of Scala Z, yes, and monad in Scala Z. So I understand that why he was explaining it. It is worth to use monads from Scala Z instead of regular monads which are in Scala. So the main point was that in case of futures, it is much easier than to just replace a future monad to some simple monad like identity. And
Yes, exactly.
Instead of writing, let's say, mocks, we define the types in a way which allows us to replace these things on, let's say, when we want to test them and we want to run into production.
Yeah.
So from the math point or computation point, or however you call it, we will have the same object, or they behave in the similar way, yeah, but the implementation, let's say, doesn't matter to us in that moment, that moment, yeah.
Yep. So this with future, it's actually a good point, because if you remember this evaluate M of this calculator, which took an arbitrary monad, you could, if you have a suitable monad for parallelism, you could just plug it in there and you could get a parallel evaluation just for free. And this is actually exactly the point. By abstracting over monads, you can just swap in a lot of different functionality. I mean, the basic idea is still the same. You have some addition or some variable access, but you can always swap out the precise means of how to perform that computation. So that's really the big value on abstracting over monads. More questions? All right, then thanks.